In this lecture, we're going to be revising the mechanics topic. So first of all, a quick recap of the most important ideas from the last lecture. In the last lecture, we were looking at orbital mechanics, and we saw that the energy of a satellite in a circular orbit could be described by the potential energy is equal to minus gmm on r. The kinetic energy is equal to gmm over 2r. Now, if this was an elliptical orbit, we just replace r with a, which is the length of the semi-major axis. And the total mechanical energy is equal to minus gmm on 2r, and again we can replace the r with a for an elliptical orbit. We also saw Kepler's 3 laws, which tells us that planets travel in an ellipse with the sun at one foci, that dA dt, that is the rate of change of area in the orbital plane, is constant, or we can say this is equal areas in equal time, and that the period squared is proportional to the radius cubed, and the proportionality constant is 4 pi squared divided by gm, where m is the mass of the sun which both the planets are orbiting. So today we're going to look at some of the big ideas that were covered in mechanics. So we saw that there's 2 main approaches that we can use when answering questions. We can consider the energy, or we consider the forces and the momentum changes. So imagine that we had a question related to this figure where we've got 2 masses with a pulley and an inclined plane. Possibly there's some friction on this slope here. If you were given a problem to solve about this situation, which of these approaches would you prefer? Okay, so there's no correct answer to this one. Each of these approaches has some advantages and some disadvantages. With the forces, you do need to consider both the components parallel to and perpendicular to the slope, though admittedly you're probably going to have to do that anyway to work out the size of the frictional force. With energy, you need to remember to account for the work done by friction. So when friction is acting, energy is not conserved, energy is lost as work done against friction. But as long as you do everything correctly, both these approaches will give you the same correct answer at the end. Okay, so a question: when is energy conserved? And you need to select all the cases for which energy is conserved. So read over these and think about which ones are correct, and then we'll discuss them. You may want to pause the video. Okay, so energy is conserved when 2 carts collide elastically. An elastic collision is one in which no kinetic energy is lost, so therefore energy is conserved. Okay, when a cannonball is launched from a cannon and air resistance is negligible, then after it's been launched, the only force acting upon it is the gravitational force. The gravitational force is a conservative force, and so energy is conserved in this case. Now, when a bullet collides with a block and it becomes embedded in the block, this is an example of a perfectly inelastic collision. During perfectly inelastic collisions, kinetic energy is lost and it is not converted to potential energy. So in this case, mechanical energy is not conserved. A block slides up an inclined plane, friction is not negligible. Okay, well, friction is a non-conservative force, so in this case, mechanical energy is lost. So now we're asked, when is momentum conserved? And again, select all the cases for which momentum is conserved. So have a read through these, think about which ones will have momentum conserved, pause it while you think, and then play the video. Okay, so 2 carts collide elastically. This is a collision. During collision, the external forces are negligible, so momentum is conserved in this case. A cannonball launched from a cannon. In this case, once it's been launched, gravity is acting upon it, which is changing its momentum, so momentum is not conserved. A bullet collides with a block and becomes embedded in the block. This is a collision where the external forces are negligible, so momentum is conserved in this case. A block slides up an inclined plane, friction is not negligible. So in this case, we have an external force, the friction, and the weight force acting upon the block. So in this case, the momentum is not conserved. So then we had a look at the demonstration where a sudden force was applied to a plate supporting an egg, and the egg dropped vertically down into the cup, and we discussed the explanation of this. So essentially what is happening is that the horizontal momentum of the egg isn't changing, as forces are not acting upon it for any significant period of time, and so it doesn't have any horizontal momentum. So when the cup disappears from underneath it, it is acted upon by an unbalanced force. There's no normal force now balancing the weight force, and so it drops down into the cup below it. Okay, so types of energy. So we've seen that there's different types of energy: potential and kinetic energy, which can be translational, that's movement through space, or rotational, where it's being pivoted about some pivot point. So these are the two types of mechanical energy. So work is one way to transfer energy from one body to another, and also convert between the two types of energy. So then we were asked which of the statements below is true. So read over the statements and pause the video, and then replay it once you've had a think about each of these. So in fact, all of these statements are true. Energy is always conserved if we consider a closed system. If we consider a system which is big enough, then there is no way for energy to get into or out of the system. So for example, the energy of the universe is constant. The energy of an object is conserved whenever non-conservative forces do no work. Again, this is true. So for example, with a pendulum, if there is no air resistance, then the energy is continually converted between potential energy and kinetic energy, but it is conserved. And the change in kinetic energy is always equal to the net work done on an object. This is also always true. So we then saw a demonstration where we dropped a little ball on top of a big ball, and we saw that the little ball bounced a whole lot higher than the big ball. So the little ball ended up higher than the drop height, and the big ball ended up lower. So one way to explain this is to consider the energy, and in this case the big ball was transferring energy to the small ball. So just after they left the ground, the small ball had more kinetic energy than it had initially, and this allowed it to get to a higher height. Okay, so a technique that came up a lot in this course was breaking an object into little components and then summing up the contribution of each of the components to work out the total force or the total energy. So here we're asked to list the types of problems that can be solved with the technique of breaking objects up into small components and then adding contributions of each of these components by integrating. So we always use this technique when we've got a continuous body rather than point particles that we're dealing with. And some of the things that we can find with this technique are total force, we can find the center of mass, we can find the potential energy, the gravitational potential energy, or we can find the moment of inertia. There may be others. If you can think of others, that's great. And then how do you solve each of these problems for a uniform ring? Okay, so let's imagine that we had a uniform ring here. Now, if we needed to consider the total force on an object a bit of a distance from a ring, what we need to do is break it up into little components. And here it actually helps to exploit the symmetry as much as possible. So we can see this component here is going to cause a force towards it, and this component up here is going to feel a force towards it. And this, if this is all drawn symmetrically, then you can see the vertical components are going to cancel each other out and the horizontal components are going to add. So what you do is you'd work out the size of the force from this component, which if it's a gravitational force would be given by F is equal to G times dm, where dm is the mass of this component, times m, this mass here, over r squared, where r squared is the distance between these two. Well, it's the square of the distance between those two. And so then, well, we call that df because that's the part of the force just due to this little component. So then we'd just work out the horizontal component, so df x, and if we had this was theta in here, this would be equal to g dm m over r squared times cos theta. And so then what we'd want to do would be to integrate over the whole ring. When we integrate over the whole ring, we'd just end up summing up all the dm's, so we'd end up with the total mass of the ring. So that's how we consider the total force. The center of mass, again, we always exploit the symmetry. So with center of mass, we can consider two little components opposite to each other, and we'd see that the center of mass for those two was right in the middle, and whichever components we consider opposite each other is always going to be right in the middle. So the center of mass would be right in the middle of our ring. For potential energy, that's kind of similar to force, but we don't need to worry about the vectors because it's not a vector. So because U is equal to minus G m on r, we again break it up into little components. So du, due to just one of these components here, is equal to minus g times m, where this is m, times dm on r, and then we'll just want to integrate these, and we end up with u is equal to minus g m times the mass of the ring on r. So for the moment of inertia, or the rotational inertia, it really depends upon the point about which we choose to pivot it. So in the lab, you worked out the moment of inertia of a disk about a point in the center, and to do that, you used r squared dm, and you came up with an expression for dm, which was the mass in this case for the moment of inertia. You're splitting it up into little rings like this little red ring here. You choose a little red ring with a thickness dr at radius r. You work out the mass of that ring and substitute that in there, and then choose appropriate limits on your integral. So have a look at your lab manual to remember how to do that one. Okay, so we saw Newton's law so many times. Newton's law is absolutely everywhere. So Newton's second law tells us that the net force is equal to the sum of all the forces acting upon the body, and that is equal to the mass of the body times its acceleration. So we could rearrange this to get our impulse equation to show how these are related. Let's write this as m dv dt. As long as we assume the mass is not changing, then we've got mv dt, and so this is equal to dp dt. So we can see that, well, f net is equal to dp dt, so f net dt is equal to dp, and then we can integrate these, and the integral of dp is the change in p. This is P initial, this is P final, so it's P final minus P initial, and that's equal to the integral of the net force with time. So that gives us our impulse equation, which is really just another way of writing Newton's second law. Now we saw Newton's second law also applies in the rotational case. So in this case, the forces are the turning forces, the torques, and the sum of all the torques gives the net torque, which is just the moment of inertia times the angular acceleration. Okay, so in this demonstration, we had two tubes. Now, the tubes actually had masses inside them. So one of them had masses a bit like this, and the other one had masses a bit like this, the same masses. And then we got two students to waggle them backwards and forwards and saw how exhausted they were after a certain amount of time. And it turned out that the student with this tube was much more exhausted than the student with this tube. So this was a nice example of moments of inertia, and again of Newton's second law, that the net torque is equal to the moment of inertia times alpha. Because this one here has a much higher moment of inertia, as the masses are much further from the point about which these tubes were being waggled, and so you had to apply a lot more net torque to this one to cause the same angular acceleration. Now, we've also been considering how we can interpret graphs. So whenever there's an integral, we can find the integral by working out the area under the graph. And if there's a derivative, then we can find the derivative by taking the gradient of the graph. So here's an example of a fairly challenging question that we could be asked about a graph. And there's always a few different ways that we can approach these questions. So the first question, what is the change in momentum of a 2 kilogram object that over the 7-second interval shown in the graph? So what we want to know is what's delta P. And one way we can do this is to use impulse, which tells us that it's equal to F dt, which is useful because if we had a force versus time graph, then we could just work out the area under this graph. Unfortunately, we don't just have a force time graph in this case, but what we can do is use Newton's second law to write the force as the mass times the acceleration. So this is the integral of the mass times the acceleration dt, which we can write as m times a dt, and we do have an acceleration versus time graph. So to work out the change in momentum, we can just do the mass, which we're given as 2 kilograms, times the area underneath this graph. So let's work out the area underneath it. Let's split it into a few different areas because we could consider this obviously as one triangle here, but for later it'll actually be easier if we split it up a bit this way. Okay, so if we consider this triangle here, it's got a height of 3 and a length of 3, so 3 times 3 is 9, and we just take half of that as the area, so that's 4.5. So next triangle is this one. This one here is going through 4.6. So this length here is 0.6 and the height is 3. So we've got 0.6 times 3 divided by 2, which gives us 0.9. Here we've got this triangle here, and this is below it. So this will be negative. And so here we've got the length is 0.4, the height is 2, so that is 0.4 as the area there. And then we've got this triangle here with a length of 2 and a height of 2, so this has got an area 2. So if we want to substitute into this to work out the change in momentum, then the mass is 2 kilograms, and we times it by these areas, which is 4.5 plus 0.9 minus 0.4 minus 2. And solving that, we end up with 6 kilograms meters per second. And let's put that as 6.0 because we'll assume that we can read everything to one decimal place. Okay, and then the second part says what would the velocity versus time look like, and we can assume that it starts from rest. Okay, so we'll want to have a velocity versus time graph like this. Here's the time, here's the velocity. Now the velocity is the area under an acceleration versus time graph. So let's sketch these times down. So 1, 2, 3, 4, 5, 6, 7. Sorry, it's not perfectly drawn. Now for the first second, it is not accelerating. So if it starts from rest, it's going to remain at rest and will have a nice horizontal line there. Between 1 and 4 seconds, it's accelerating, and the acceleration is at an increasing rate. So we can see from the area under the graph, which gives us the velocity, that at 4 seconds, its velocity should be, this is 4.5 meters per second, and that's at an increasing rate. So this is actually a parabola where it's curving up and going through there. Now between 4 and 4.6 seconds, so let's put 4.6 here, we've still got a positive acceleration, but it's at a decreasing rate. At 4.6 seconds, the acceleration is 0. So we can see that the velocity is going to increase by another 0.9. So 4.5 plus 0.9 gets us up to 5.4. So, sorry, this is really not to scale. So that's up to 5.4 there. And so this is going to be another parabola, but it's bending in the opposite direction. And then between 4.6 and 5 seconds, its velocity decreases by 0.4. So we're going down to 5 meters per second. So that's like this. And it's at an increasing rate, but in the negative direction. So we have a parabola which is bending round like this. And then between 5 and 7 seconds, the magnitude of the acceleration is decreasing, but it is in the negative direction. So even though the velocity is still positive, that's slowing. And so in this time, it slows down 2 meters per second. So we're going down to 3 meters per second here. So this will be another parabola which looks like this. So that's a rough sketch of what the velocity versus time graph would look like. So next we had a look at this possibly slightly surprising demo where we had a cup and a ball on a length of rod here. Now the cup is actually screwed to the length of rod, whereas the ball is free to move, and we knocked this supporting piece of metal, which is actually a ruler, out of the way, and we saw that the ball actually landed in the cup. And we discussed how that could work because at the moment they're not aligned horizontally, but of course the cup undergoes circular motion as it comes down, and the ball just experiences the gravitational force, so falls down like this. And so then we're asked, how could you calculate how fast the pole is moving just at the end of its motion? Okay, so if we make the assumption that the pole has uniform density, then we can model all its mass as being at the center of mass here, which is halfway along the pole. So let's call the length of the pole here L, and we'll call the height of the center of mass here H, and we'll call this angle in here theta. And the only forces acting once it's been released are the gravitational force. So we can say, well, energy is conserved. And so we've got U initial plus K initial is equal to U final plus K final. The initial kinetic energy is 0 for the end of the pole because it's at rest. The final potential energy is 0 because it's coming down to this horizontal position with height equals to 0. So we've got mgh is equal to, now in this case, this pole is pivoting about this point here. So rather than having translational kinetic energy, it's got rotational kinetic energy. So that's equal to a half I omega squared. And for a rod pivoted about one end, we've shown that I is equal to a third ml squared. So we can substitute this in, and we've got a half times a third ml squared times omega squared, and that's equal to mgh. And h here is the height of the center of mass. So this is right in the middle of the rod. So this is L on 2. So hopefully you can see from here that h is equal to L over 2 sine theta. So we can cancel out the m's, and then we'll put g times L over 2 sine theta is equal to a half times a third L squared omega squared. So the halves will cancel out, and we can now use V is equal to omega r, and in this case the radius is L because we're considering a point on the end of the rod here, so this is equal to L. So we can write GL sine theta is equal to L squared on 3 times omega squared, which is V squared over L squared. And so these L squareds cancel out, and we end up with V squared is equal to 3GL sine theta, and so the velocity is equal to the square root of 3GL sine theta. So we could use this to work out the velocity of the end of the rod just before it hit the ground. Now, if for a comparison we want to work out how fast this ball is going, the ball is not connected to the rod. So we can use v squared equals u squared plus 2as. Now it starts from rest, and s is this height here. Let's draw it in green. It's this height. This is length L. So this height is given by L sine theta. So we can say, well, v squared is equal to 2. Now, the acceleration is due to gravity, and the displacement is L sine theta. So you can see the velocity of the ball is given by the square root of 2g L sine theta. So the cup is actually moving slightly faster than the ball at the bottom here. Okay, so another thing that we looked at was this apparatus here, and we thought about how we could calculate the acceleration as that hanging mass dropped. So essentially what we have is an almost massless rod with a mass here, let's give it lowercase m, and a mass here, same mass, and we'll place them at a distance capital R from the center of the rod. And then this rod is connected around a kind of fattish, again, we'll assume it's massless beam with a radius little r. And then we've got a string wound around here with some hanging mass, which we'll call capital M here. Now, if we assume that these two rods are massless, then the moment of inertia of this system, it's just 2-point masses, and we'll call them both a distance r from the pivot. So the moment of inertia of the system is given by 2mr squared. And so we can use Newton's law to write down, Newton's second law, to write down equations for the hanging mass and also for the 2-point masses here. So for that hanging mass, we've got a tension app. So we've got MA is equal to mg, which is pulling it down. So let's draw a little free body diagram. We've got mg pulling it down, and we've got the tension force pulling it up. So this is minus tension. Now the tension here is acting as a turning force. So the tension is up against here, and this has got radius little r here. So the torque, which is causing these two masses here to turn, is caused by the tension force. So we can use Newton's second law for rotation to write I alpha, which is equal to I is 2m r squared. Okay, and then we've got the angular acceleration, and we can write the angular acceleration as alpha is equal to the acceleration over, we're looking at the acceleration here, the tangential acceleration at this point, so this is over little r. So this is times a over little r. And this, according to Newton's second law, is equal to the net torque, and the only force which is acting to apply the torque is the tension force acting here. So that's equal to r, it's lowercase r here because it's acting at this smaller radius, times the tension force. Okay, so let's divide both sides of this part by r. So we've got that the tension force is equal to 2mr squared a over r squared, and we can now substitute that back into this equation here. So here we've got mg minus 2, this is lowercase m, these masses here, times r squared a over r squared. So we want to rearrange this to get the acceleration, so we'll move this over to the left hand side, and we've got the mass times, well, plus 2mr squared on r squared times a is equal to mg, and so we've got the acceleration is equal to mg over m plus 2mr squared on r squared. And this gives us an expression for the acceleration of this hanging mass as it falls. So then at the end there was a chance to ask questions, and next lecture we'll be starting the thermal topic.